Okay, we're going to start looking at a new unit today called optimization. So we're going to break it into two parts, and today's going to be part one. Optimization means to optimize something, right? So that means we're really looking for like a maximum. Maximum. I guess maybe a minimum. No, we're looking for a maximum. Okay, so these are kind of cool because they're all real life examples. And we're just going to dive in because there's no easy way to go through this. All right, so question one, example one. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fencing along the river. What are the dimensions of the fence that has the largest area? Okay, so let's draw ourselves a picture. Step one is always draw a pic, right? These are all going to be different and they will hinge on a picture. So we've got a straight river. Okay, so it means it makes a straight line. He has 2,400 feet of fence and wants to fence off a rectangular field that borders a straight river. So he wants a rectangular field that borders the river. He needs no fencing along the river because, duh. Actually, I had somebody tell me once that their cows would wander into the river and then drown sometimes, or they'd have to go try and rescue them. So maybe you should have a fence along the river. But anyway, okay, focus. So what are the dimensions of the fence that has the largest area? So the second thing we're going to ask ourselves is, what are we trying to maximize? What are we trying? Is that how you spell trying? To maximize. Okay, so let's read this one more time. What are the dimensions of the fence that has the largest is our keyword here, area. So we are trying to maximize area, right? Not the dimensions of the fence, but the area. Okay, so we need to max area. Okay, now here's the question. How do you find the area of a rectangle? What is the formula for area of a rectangle? Well, the formula is length times width, right? And this is my width. Okay, there's my width. And so then this is our length. Okay, so what else do we know? This is asking us about 2,400 feet of fencing. Well, what is that number? That represents perimeter, right? So what do we know? So what do we know? Okay, we know here that perimeter, how do we find perimeter? Perimeter is, in this case, don't we have a length here as well? So if we were going to find the perimeter, we'd have length plus width, right? So that's really two lengths. So the perimeter is 2L plus W. And don't we know the perimeter? It has to be what? We were given that number. It has to be 24. So I'm going to actually erase this P because I know the perimeter. It's 2,400. Okay, so here's what we've got so far. We know what this thing looks like. We know that an area, a max area, is what we're looking for, and we've been given a perimeter. So what can we do? When we think about the word maximum, what does maximum mean? It means derivative, right? Isn't where your derivative is 0? That's your maximum? Duh. Okay, so how can we make this work for us? What are we trying to maximize? We are trying to maximize this guy, which means we need the derivative of it. But taking the derivative of this is not going to work. So let's make a note of what we need to do. We need a derivative, okay? So what we can do is we're going to take the perimeter that we know and we're going to rework it. And we're going to solve it for either, we're going to rearrange it and make it equal either W or L. Doesn't matter which one. W seems like it'd be faster. And then we're going to take it and we're going to plug it in here. Then we'll just have L's and then we can find the derivative. Okay, so let's rearrange this guy. So I'm going to say 2400 minus 2L equals W, right? And then if that's the case, I'm going to plug that in to my area formula. So my next step is going to be, okay. My next step is going to be plug into other equation. Okay? So I'm going to say that area equals length, right? Length times width. Well, what is width? Width is 2400 minus 2L. So times width. So 2400 minus 2L. Okay, so that's all I did. I plugged it into my other equation. I'm going to really quickly distribute that because my next goal is to take the derivative, right? If I want a maximum, I need to take the derivative. So I'm going to multiply this through, and I'm going to say A equals 2400L minus 2L squared. And then if I take the derivative of that, A prime equals 2400 minus 4L, right? And then what do I know about finding a max? Max exists where the derivative equals 0. So 0 equals 2400 minus 4L. So I'm going to keep going over here. So negative 2400 equals negative 4L. So then negative 2400 divided by negative 4 equals L. So L equals what? 600. 600. Okay, boom, look at that. So that means that if I come back up here to my picture, my lengths have to both be 600, right? And if my lengths are 600, 600 plus 600 is 1200, then what does my width have to be if my total is 2400? This has to be 1200. And boom, there's my dimensions. Those dimensions will give me the absolute greatest area. Okay, and so what were we asking? What are the dimensions of the fence? So we asked for dimensions of the fence. So therefore it's 600 by 1200 meters. And if we were asked for the area, well then we would just figure that out. 600 times 120 is, 720,000 meters squared. But it was asking for dimensions. Okay, see how that works? So here's what we did. We drew a picture. We figured out what formula we had that we were trying to maximize. In this case, it was area. We also wrote down the formula for what we knew. In this case, it was perimeter. We rearranged and plugged it into the other equation. So I rearranged perimeter to plug it into area. I took the derivative of what I was trying to maximize, set it equal to 0, solved it. There we go. All right, let's try another one. Okay, this one is similar. I know I said they wouldn't be, but they are. Okay, we need to enclose a field with a rectangular fence. We have 500 feet of fencing material, and a building is on one side of the field, so it won't need any fencing. Determine the dimensions of the field that will enclose the largest, typo, area. Okay, so this is just like the last one. So we've got like some sort of building, right? Building. Does that look like a building? That does not look like a building. It's brick. Okay, there's your building. Okay, and we want to enclose a field. Okay, so fields are green. Okay, and we need a rectangular fence. So we need a fence. Oops. We need a fence coming off the building into the field that's a rectangle. And we have 500 feet of fencing material, so 500 feet total. Okay? Determine the dimensions of the field that will enclose the largest area. Okay, so I drew my picture. Now my question is, we want to maximize area. Well, what is the formula for area? A equals L times W. So if we go back and do that, we've got, let's see, width, and length, right? And that's what we're trying to maximize. What do we know? We know perimeter. Well, what does our perimeter equal here? It equals 500, which equals 2W plus length. Okay, I want you to hit pause and see if you can solve this thing. Okay, are you back? Okay, cool. All right, so our next move is going to, remember, this is what we're trying to maximize. We're trying to maximize this guy. So we're going to take our perimeter and we're going to rearrange it, and I'm going to solve for L. So I'm going to have 500 minus 2W equals L. And the reason we're doing that is that so we can substitute it in and then only deal with one variable. Okay, so now we're going to substitute that in, and we're going to say A equals L. Well, L is 500 minus 2W times W. Okay? I'm going to distribute that, make my life a little easier. So 500W minus 2W squared. And then, because we're looking for maximum, we need to take the derivative. So A prime. So the derivative of 500W is 500. The derivative of negative 2W squared is negative 4W. Okay? Set that equal to 0. 0 equals 500 minus 4W. Negative 500 equals negative 4W. Divide out your negative 4. And what's 500 divided by 4? 125. So 125, I think we're dealing with feet. That equals our W. Okay, so if this is 125, and this is 125, that adds up to 250, which means our length has to be 250 feet. Wow, that's not how you spell feet. Okay, so our largest dimension, or the dimensions that will give us the largest, is going to be 125 by 250 feet. Okay, not bad. Okay, so let's do one more, but let's reverse this, and let me write this out for you. Okay, so you got 15 chickens, okay? And the farmer says you need 300 square feet for these chickens, of an area for them to run in. So you need the minimum amount of fence, right? Because fencing is expensive. So you need the minimum amount of fence. And it needs to be a rectangular area. So the minimum amount of fence for a rectangular area. Okay? So here's our question. You've got 15 chicks. You need 300 square feet. So this is area. So this time we know our area. You need the minimum amount of fence. Well, that is what we're looking for, right? So what are we trying to maximize here? Or I guess minimize, which is still optimizing. So this time we're trying to minimize the amount of fence is perimeter, right? And how do we find perimeter? Well, 2L plus 2W, because we said this was a rectangular area. So L, L, W, W. Okay, area, what do we know? We know area. I'm going to put a star here because this is what we're trying to minimize. We know area. Area of this rectangle is L and times W, and we know that that's 300. So 300 equals L times W. So we're following the same process this time. It's just we're trying to minimize perimeter. So before our next step we know is to substitute into whatever we're trying to minimize. So that means we need to rearrange our area equation so we can substitute it in. So do you want to solve for L or W? Let's solve for L. So we're going to have 300 divided by W equals L. Okay, so I'm going to take that and I'm going to substitute it into here. All right, so I'm going to say P equals 2L. Well, L is 300 divided by W plus 2W. And then I'm going to take the derivative of this because I need to know the optimum measurements. So I'm going to multiply this through and then I'm going to take the derivative. So that means I'm going to have P equals 600 over W plus 2W. Well, if I want to take the derivative, I can see some quotient rule, and I'm going to avoid that. So I'm going to go ahead and say P equals 600W to the negative 1 plus 2W, right? That's way better. Okay, so now we need the derivative. Well, what is the derivative of 600W negative 1? It's negative 600W to the negative 2 plus 2. Okay? We need to set that equal to 0. And I'm going to clean this up. So negative 600 over W squared. It's going to make my life easier. Plus 2. Now we're solving for W. Move your 2 over. Negative 2. I'm going to multiply this W squared up. So negative 2W squared equals negative 600. Okay, now I'm going to divide out my negative 2. And then I'm going to take the square root, right? So negative 600 divided by negative 2 is 300. The square root of 300. What is the square root of 300? 17. So W equals 17.3. Is that what we got? 17.3. Okay, so here is my width. 17.3. So if my width is 17.3 and I know my area is 300, then now can I just find my length, right? 17.3 times what equals 300? Oh, I know, 17.3. Okay, so therefore our length is also 17.3. Okay, so we did basically the same problem. We just reversed what we were trying to maximize. It did not change our process. We still had to figure out the formula for what we were trying to optimize. We figured out our secondary formula that we knew we had some given information for. We rearranged it. We substituted it in. We took the derivative. We set it equal to 0, and we solved. That's all there is to it. Good luck.